In this video clip, I will explain few statistical metrics that is very useful for selecting the size of your subset. So as I mentioned earlier, the simple RSS value is not good metric because RSS value always decrease as you increase the number of input predictors. So people use some other statistical metric that consider the number of predictor. The first one is CP. CP is RSS plus 2D times sigma hat square. The sigma hat square is the estimated variance of your observation noise epsilon I, right? Some textbook include 1/n normalization factor, but this is not important because you just compare the CP value for different size of model. So the same constant factor in front of your CP value does not change anything. So for example, so in your first stepwise selection, at the first stage, you compute the CP value. So here the D is the number of parameters. I just follow the notation in our textbook and our official the YouTube lecture slide. Okay, so for instance, in the first stepwise selection, we have the stage. At the first stage, the D is equal to 1. You only have beta 0. And with only one parameters, you find the best model and RSS value you compute. But in this case, because D is equal to 1, you just need to plus sigma hat square. At the second stage, when D equal to 2, you will have different RSS value. So let's say this is RSS1, this is RSS2. And since you use the model having two parameters, this will be 2 times sigma hat square. D equal to 3 as well, RSS3 plus 3 sigma hat square. And just compare these values, the CP values, to choose the best one. So in the CP value, RSS part always decrease. As you increase the number of parameters or number of input predictors, your RSS value always decrease because you have more degree of freedom, so you can more nice fitting model for your training dataset. But this term will increase as you increase the number of input predictors or number of parameters. So the summation RSS plus D2D times sigma hat square, RSS plus 2D times sigma hat square will make some U-shaped curve. Okay? And then from the U-shaped curve, you can find the best set size. Okay? So if you just use RSS value, you definitely go to the full size of input predictor because RSS always decrease. So CP introduced this additional term which take into account the size of your input predictors, and this linearly increased part makes some U shape of CP curve, and from that you can find some nice set size. Okay, but one remark here is CP cannot give you the best subset size, which is just some nice guide, right? So in practice, if you follow the CP rule, usually you can have very reasonably nice set size, and you can expect some reasonably nice test error. but this does not guarantee the best model. Okay? And this is CP. And AIC model, essentially almost the same with the CP model. This is equal to minus 2 times log L plus 2 times D. Here, L is the likelihood value. Likelihood value is very important concept. So here we use likelihood function for your given model. Essentially, when you have a parameter beta, you have some prediction model, right? Fx is equal to beta 0 plus beta 1 x1 plus beta p xp, right? So if you have parameter beta, you have this prediction model. And your assumption is, or general assumption for linear regression is yi followed fxi plus epsilon I observation rule. So here epsilon I is independent Gaussian noise with mean zero and variance sigma square. So the probability of your data set, so data set means all your collection x1, y1, x2, y2, up to xn, yn, which follow this distribution, the products, because every observations are independent. This is equal to product I1 to n 1 over square root of 2 pi sigma exponential minus 1 over 2 sigma square yi minus fxi square. Because here the likelihood function means if the true model follow the parameter beta, what is the probability of your crowd observation? So because beta 0 to beta p are true parameter, ground truth parameters, the difference between yi and your function fxi comes from the observation noise epsilon I. And since epsilon I are independent Gaussian noise with mean zero and variance sigma square, the likelihood function is this product of the Gaussian noise probability. Okay, so when you take the log, this is this minus 2 times from the very nice property of log AB is equal to log A plus log B. This is equal to minus 2 times n times log 1 over square root of 2 pi sigma plus minus 2 sigma square summation yi minus fxi square I1 to n. Right? So here the log is actually ln. Okay? And this part is RSS. This part is RSS. Okay? And we have n here. And log 1 over 2 pi sigma square here. But here we have very important part, which is basically this term does not depend on your parameter beta. And this term does not depend on your model. Okay, no matter which size of your subset, this value always a constant. So when you compare your fourth stepwise selection, the case D is equal to 1, D equal to 2, D equal to 3, and D equal to 4, and so on, the AIC value will be equal to some constant, because this is just constant, plus 1 over sigma square RSS and 2D plus 2D. Okay, and this constant always added to each stage, so you can simply ignore this part. And when the sigma square is equal to sigma hat square, essentially you can multiply the sigma square to the every stage, which essentially becomes RSS plus 2D sigma square, which was CP value. So that's why in our textbook and in many places, people say CP almost same with AIC, especially for the linear regression with normal Gaussian noise. Okay. The next one is BIC. So we can use BIC metric as well. The BIC model is compute 1 over n times RSS plus log n times d times sigma s square. So the only difference between CP and BIC is CP was RSS plus d times sigma s square. So the BIC have this additional factor here, so which means BIC penalize more on the model with many variables, especially when the number of input data points are high. So when log n is much bigger than the constant, then we have a very huge penalty for increasing the number of input predictor. And the BIC, essentially the BIC B comes from Bayesian. Sorry, this was 2. So what is Bayesian? Bayesian is simply this. Probability A for given B is equal to probability B given A times probability A over probability B. So this is the Bayesian rule. Why this is interesting? So in the previous case, likelihood case, we compute the probability for your data point for given parameter and model. But some people are more interested in the probability for your parameter or model for given data point. For your given data point, what is the probability your ground truth model is equal to the beta? Okay, so this is more interesting in some cases. But the problem is, this is extremely difficult to compute. And we need some additional assumption as well. From the Bayesian rule, we can rewrite this conditional distribution as like this. Probability data for given parameter or model, probability your parameter, probability data. This extremely difficult to compute. So instead of calculating this value, we usually use this simple trick. Since we are interested in the max beta that maximize this conditional distribution for your given data point D, this is equal to max beta probability D for given beta times probability beta. Why? Because this denominator always the same for every model, because this is probability of your observed data and this is given. Yeah, I mean our data is given, so whatever you choose for the model, this probability always the same. So we just need to consider this part. Okay, so this is very important. Here, this part is prior on your model or on your parameter. This part is just likelihood value, right? This is just likelihood probability. So the Bayesian, basically, the main difference between Bayesian and likelihood method is in the Bayesian we have prior distribution and we utilize the prior distribution for estimating our parameter and our outcome. That is the main difference. Okay, anyway, so BIC used this Bayesian rule, and from the some prior distribution, BIC value include the log n term, and essentially because of this log n term, BIC metric penalize more when you increase the number of parameters. And it is very hard to say which metric is the best, which really depends on your data point and situation. And I think everything is fine. You can use AIC, you can use BIC. It's very up to you.